Hey, happy Thursday to you all. I'm here in Archbold. It's nice and sunny today, 70 degrees. I'm done testing. So I wanted to see you guys live so you can see me, but I can't see you. So this is a short video on specific heat just to go over the test questions, just to understand what specific heat capacity is. So just wanted to say hi, hey, and I'm going to take my face off of here for now. All right. So, what is specific heat capacity? So, this fish is saying, I love the specific heat, the capacity of water. So, why would the fish say that? We'll talk about that toward the end. We will demonstrate understanding how a measure for specific heat. I will evaluate the relationship in specific heat equations. So there's some equations in here which you won't have to do in the test. So, but just everything in physics and science has a lot to do with math. So that might upset some of you, but it's just the way that we quantize things so that we can organize our life because they're predictable. So when it's predictable, there's some math involved here. So let's say that we heat up rods of lead, glass, aluminum, copper, and iron to 100 degrees. So there's a fire underneath all these, and so they're all 100 degrees, and this is the time it takes. So this is a different kind of demonstration. So this is the time it takes: 37 seconds for lead to heat up, 52 seconds for glass to heat up to 100, 60 seconds for aluminum, 83 for copper, and 90 for iron. So this is the heat capacity based on the time to heat this from 0 degrees, so cold, very cold, 0 degrees Celsius to 100. And so which has the highest heat capacity? So, and everything, depending on the size. So if you think about if you're boiling water, if you have a small amount of water to boil, it boils faster than a large amount of water. So again, all these rods are the same size, right? And you're only seeing the end of the rods. So all of them are the same size, okay? And that way you're not because it's certainly if iron was a bigger piece, it was going to take a lot longer to heat up. But it does. It takes so heat capacity is basically we've figured out how much energy it takes things to heat up, and that's useful for a lot of reasons. And we've talked about that in the past, but I'll just kind of go over this here real quickly. So here is what happens. So as we put these metal rods on some wax, and you'll see, well, these are actually balls, but I'm going to show you a video of rods. So the iron has melted all the way through, the copper all the way through, the aluminum halfway through, glass barely makes a dent, and so is lead. So let's show you this video over here. Pause a second. So I'm going to show you this. Let's go. It does not have any sound to it, so let me show you what this is. Okay, I'll load this up so you can see it. So we have different rods, and here's wax. So we're going to turn this on. The specific heat is the amount of heat per unit mass required to raise the temperature 1 degree Celsius. So we put this copper to aluminum in boiling water, and we put the aluminum, and you'll see it's melting, but it's not melting very far. And then we put some a copper piece on the same amount. So remember, they were all both the same temperature, 100 degrees. Okay. And it is moving down a little bit further, not much further, but you can see that the puddle that the copper made was bigger. So if we take a look at this, 689 joules for aluminum and 900 and so forth for, so if I put this back, let me back this up a little bit. Okay. And pause a second. So we have copper, stainless steel, iron, and aluminum. All right. So the they melted different amounts here. So these were all the same temperature, boiled in the water. It looks like the iron went down the furthest, right? Steel pretty close to that. Aluminum not as far, and copper not as far. So um, this is just a demonstration of how these work. So if we take a look at, let me stop showing this here. If we take a look at what happened, iron went all the way through, right? We had copper going through. So the specific heat numbers on those, okay, so let me go here. All right, some objects are easier to heat than others. When heat flows into an object, its thermal energy and temperature increase. The amount of increase in the temperature depends on the size. So again, boiling water, small amount of water will boil faster. So if the sizes of those pieces of those iron balls will make a difference as well. But the material itself has bonds between them, and metals heat up faster than most things anyway. So, and we want that to happen so we can have a fry pan that'll cook fast, heat up fast. So a lot of times we use aluminum on the bottom of a stainless steel pan in order for that to work. So, so specific heat capacity will change depending on the state of matter as well. Temperature remains constant until the phase change is complete. So again, this is, we've talked about that freezing and melting. So at 0 degrees, if we lower the temperature, it starts to turn into a solid. If we raise the temperature from 0, it will melt and turn to a liquid. So this phase change talks about the intermolecular bonds, the bonds between individual water molecules, keeps this at 0 until all of it is melted, until it's completely water. And then at 100 degrees Celsius, water and steam are created here. The 100 degrees, it stays again until the bonds between the molecules breaks, stays at 100, and then until it turns into gas. All right, so if you think about the specific heat of something, we use this Q equals mass times the constant times the change in temperature. So Q is the heat absorbed in joules, the specific heat constant. It's a number that we've scientifically figured out, and it's a list, and then the mass and the time temperature change. So let's take a look at this. Liquid water has a very high specific heat compared to specific heat of other substances. So again, so remember we said that iron was 450 and copper was less, 385, right? So that's why when it released its energy, iron released its energy into the wax, it melted it further. So it took longer to heat, but it also takes longer to release the heat, right? Copper didn't take as long to heat, and it released energy, but it did not release as much energy. Aluminum has so aluminum has a higher heat capacity than copper or iron. So that's why we use it. Takes a while longer to heat up, but it also stays hot longer. And lead is the least amount of energy needed to raise its temperature, and it releases the same. It releases it quickly. So you can see that water has a high specific heat, takes 4,180 joules to heat water up to just 1 degree. All right, but ice 2,060. So at that, so even states of um, phases can make a difference in the specific heat of things. All right, so this is where you would figure out the specific heat of a substance. But we're going to stop at this point, and not do these experiments. You would do these experiments in a physics classroom or a chemistry classroom when we talk about these things. Okay, so let's take a quick quiz on this. Which will heat up the slowest? Okay, so if we look at iron, it's 0.45 for specific heat. Lead is 0.13. Granite is 0.79. And water is 4.18. So heat up the slowest. So the bigger the number, the slower it heats up. Okay, so we're going to click on that. All right. Eraser. Oh, cool. I get some bonuses. All right. What would the effect on the particles if the more heat is supplied to a system? So they would stop moving. No, wouldn't stop moving. That would be taking energy away. It would have some effect. It doesn't have. They wouldn't slow down because taking heat away will slow it down. But energy would speed things up. Won't use my booster here. If I heat up 2 pans of water, one has 100 milliliters in it and one has 1,000 milliliters, which will heat up faster? Well, as we said, in the specific heat, the less water you have, the quicker it will heat up. Doing good so far. Which of the following best explains why sand at the beach is hotter than the water? All right, the more sand on the beach than there's water. No, that's not the case. There's more water than sand. There's more water than sand on the beach. The sand is a lower specific heat. The sand has a higher specific heat. So it has a lower specific heat is the best answer there. So that means it heats up faster, right? The amount of energy required to raise the temperature of 1 degree of a gram is called specific heat. That's what we called it. 1 gram of the material to raise it 1 degree is a number they give it, and they give that number a specific heat. They try to make everything the same size, so we talk about 1 gram of something. Compare it with another 1 gram. When a piece of aluminum foil is taken out of the oven, cools from 100 to 50, what's the change in temperature? Well, that's a 50-degree change in temperature, right? How does heat flow? Okay, if you haven't figured this out from now, it goes from warm to cold, always warm to cold, never cold to warm. Mia's getting up really good. Which will heat up the fastest? All right, and okay, so we have different substances. So we're looking for the smallest number to tell us which one will heat up the fastest. So we've got copper at 0.38, granite at 0.79. So copper's smaller number than granite. Basalt, 0.84. So that is bigger than granite, and iron is 0.45. So it's copper that'll heat up the fastest. Now, copper will release less heat because it heated up quickly. The specific heat of water is 4.18 joules per gram. Specific heat of wood is 1.76 joules per gram. What material needs more heat energy to raise its temperature? Okay, so we're going to say water because the number is bigger. It takes more energy to heat up the water. Right? Copper, stainless steel, carbon, and zinc are all heated up at the same thermal energy. What material would be the coolest after being heated? Okay, so the lower number, so this one is talking about kilograms. That's why the numbers are bigger. So copper has 385, stainless steel has 477, carbon steel has 490, and zinc has 380. So zinc has the lower number, so that means it'll heat up faster and it will cool off faster. Oh no, what did I miss? A carbon steel. Okay, I messed up. Oh, guys, I'll have to look at that one again. Either that or they got it wrong. All right, carbon, copper, stainless steel, zinc are all heated at the same thermal energy. What material would be the coolest after being heated? All right, let's see if I'm good at this one. I'm still saying, what did I see? Zinc was 380, carbon steel was 490, copper was 385, and stainless steel was 477. So I'm still going to say zinc in this particular case. Copper was, let's try, carbon steel, 490. Okay. So I obviously am having trouble on this particular one. Sorry about that, guys. I will double check that one out for you. All right, so I figured out what my mistake was, ladies and gentlemen. So copper, stainless steel, and carbon steel and zinc are all heated with the same thermal energy. Okay, so the same amount of thermal energy. All right, so not that they're all the same temperature. So which will be the coolest? Okay, so carbon steel will be the coolest because it has the highest energy specific heat, right? So if they're all heated with the same amount of energy, and so basically like the same amount of time heating with the same amount of heat source, carbon steel will, because it's 490, will be one that heats up and be the coolest. All right, just read that wrong. Thanks for guys for bearing with me.